You're planning a journey to go somewhere far from home, perhaps somewhere you've never been to before. You know where you want to go, but you don't know how to get there. So you have to start planning. Maybe you use something static like paper maps, or you use something that can update your route based off of changes in the road or changes on traffic conditions, something like a map website or a GPS app on your phone. And then after all that planning, you set out on your journey. And at every intersection you come to, you have to make a decision. Which road will get you closer to your destination? Now, you do all of this travel across neighborhood roads, city streets, and even across stretches of high-speed highways. And eventually, you reach your destination. Now, just like you did all your planning and made all your decisions, when an IP packet has to take data across the network, it starts in its local subnet, its neighborhood. It moves on to the local area network, even into an ISP or an internet service provider's network, and then eventually, depending on where it's going, across the internet and the internet routers. At every point, every router it gets to, every layer 3 device that it gets to, a decision has to be made. What is the network that will get it closer to its destination? This is all handled through IP routing. Hi, my name is Rich and welcome to the Rich Tech Guy channel. And in this video, we are going to take a look at IP routing and how traffic moves across the network at layer 3. But first, I'm going to bring up a little bit of a prerequisite. In order to understand IP routing, you first need to have a very firm understanding of IP addresses and subnetting. So, if you need a refresher on that, or you need to build up your skills on that, I'm going to encourage you to go watch my video on IP addresses and subnetting, which I will link to up above and in the description below. So if you need that refresher, go ahead and watch that video. I'll wait for you to come back. All right, are you back? So let's get into IP addresses or IP routing. But first, why don't you go ahead and hit that like button? And if you're not subscribed to this channel, go ahead and hit that subscribe button too. Actually, according to YouTube metrics, 92.5% of you guys watching are not subscribed to this channel. So please go ahead and hit that subscribe button. And with that, let's get into IP routing and how we can move packets across the network. What is IP routing? IP routing operates at layer 3 of the OSI model, and it is the process of getting your packet from its source to its destination. All right, now if you recall from my IP subnetting video, if the destination IP address is in the same subnet, then your computer or device that is the origin of the IP packet will simply send it to the IP address of the destination and everything is complete. In a manner of speaking. There are some layer 2 processes that if the data happens to go through a few switches along the way, but that's a topic for another video. But what happens if that IP packet destination is outside of the subnet from the origin device? That's where we need to bring IP routing into play. And you may recall from my subnetting video, I referenced a default gateway, which is where your computer would send that packet to if it was outside of its own subnet. But that's really only the first step. So let's start digging further into it by taking a dive into IP routing. So I have a simple network with 2 routers. Each router has its own local network, and I have a host on each network. Router 1 is the gateway router for the 192.168.10.0/24 network. Its IP address on that network is 192.168.10.1. Host 1 is on that network with the IP address of 192.168.10.10. It has its default gateway set to 192.168.10.1. the IP address of the router on that network. Router 2 is the gateway router for the 192.168.20.0/24 network. Its IP address on that network is 192.168.20.1. Host 2 is on that network with the IP address of 192.168.20.20. It has its default gateway set to 192.168.20.1, the IP address of the router on that network. Between the routers, there is a point-to-point link on the network, which is the 10.10.10.0/30 network. On this network, router 1 has the IP address of 10.10.10.1, and router 2 has the IP address of 10.10.10.2. So I'm going to test my connectivity by having host 1 ping its default gateway 5 times. Now host 1 is a Linux system, and in Linux, if you use the command ping IP address, it will continue to ping indefinitely until you cancel the command by pressing Ctrl+C. On Linux, if you want to send a specific number of pings, you will use the -C option followed by the number of pings, then the IP address. Think of -C as a count of the number of pings you wish to send. On a Windows machine, the ping command will default to send 4 pings. If you want to send a different number of pings, you will need to use the /n option followed by the number of pings. Think of the n as the number of pings to send. Also, on a Windows machine, if you want to ping indefinitely, like a Linux machine, you will need to use the /t option. I don't know why they went with /t, but it's Windows. Things don't have to make sense in Windows. Sending 5 pings from host 1 to its default gateway address on router 1. The pings work. Okay, so now let's send from host 2, and I will ping its default gateway. Again, the pings work. I can also have the host 1 ping the point-to-point interface on router 1. And again, the pings work. So host 1 can send its packets to the default gateway to be routed out to other networks. And now I'm going to have host 1 ping host 2. And notice that the pings don't work. I get the message, destination host unreachable. So we know that the host can successfully ping its default gateway. We also know that the host can ping onto the network between the routers, but it cannot ping the router for host 2. So let's take a look at router 1. All right, so now we're on router 1, and I'm going to put in the command show IP interface brief. There are 2 connections, one to the host 1 network and one to the point-to-point network connecting the other router, and both links are up, so the connections are there. But now let's take a look at another show command on router 1. I'm going to input the show IP route, and this will bring up the routing table. Now I will go into the routing table in more detail later in the video, but our answer to why host 1 cannot ping host 2 lies right here. The routing table lists every network that the router knows about. Or more accurately, and I will get into this later, the router lists every network that the router prefers to use. So if it has multiple knowledge of networks but knows there is a better network, it will only put that network into the routing table. Now as we look at this routing table, we can see that the router knows about 2 networks. It knows about the host 1 network, and it knows about the point-to-point network. But there's no information about the host 2 network. This is why our pings aren't reaching host 2. When host 1 is sending a ping to its default gateway address on router 1, with the destination IP of host 2, router 1 receives the ping, but has no idea where to send the packet, so it dropped it. Now, why does router know about the host 1 network and the point-to-point network, but not the host 2 network? And that's because it is directly connected to the host 1 network and to the point-to-point network. But the host 2 network is behind router 2. And router 1 doesn't know about what is beyond router 2. In order to solve this, we need to tell router 1 about any networks beyond router 2. And we are going to do this with a static route. When we program a static route on a Cisco router, we are going to use the IP route command. Now the command is IP route, the destination network address, the subnet mask of the destination network, and then the next hop address. Okay, there is another way you can input a static route, and it would be IP route, destination network address, subnet mask of the destination network, and then instead of the next hop address, you would put the exit interface on the router. However, there are issues where that particular static route command could lead to problems with routing. So the preferred way to say it, or the preferred way to input the command, is IP route, destination network address, the subnet mask of the destination network, and then the next hop address. So the IP route command is a config level command. And to be able to use this command, I will first have to type in config terminal, or conft for short. The command I'm going to type into router 1 is IP route, and then I'm going to do the network address, which is 192.168.20.0, the subnet mask, 255.255.255.0, and the next hop address of 10.10.10.2, the address of router 2's interface on the point-to-point network. Keep in mind, you have to use the network address, okay? If you don't, if you use, let's say, 192.168.20.1, the router will give you an error. So it has to be the network address. After entering that command, let's take a look at router 1's routing table. Now we see a new line for the host 2 network, 192.168.20.0. And the router is saying that to get to this network, it needs to send packets to 10.10.10.2, which is the interface for router 2 on the point-to-point network. So let's go on to host 1 and ping host 2. And we're seeing nothing happen for a little bit here. And it doesn't work. But it no longer says that host 1 is or the destination host is unreachable. Instead, it just blanks out, and at the end it says that 5 pings were sent and 0 received. Why? Well, it's because we've only solved half of the problem. So if we were sending UDP packets from host 1 to host 2, the problem would be solved because UDP is one-way traffic. Instead, when we send a ping, we are sending ICMP packets, which require a reply. So what's happening is that host 1 is sending the ICMP ping to host 2. In order to do that, it sends the packet to its default gateway address, which is on router 1. Router 1 is now informed of host 2's network through the static route and knows to send the packet to router 2 across the point-to-point network. Router 2 receives the packet and knows about host 2's network because it is directly connected. And it sends the ICMP packet to host 2. So far, everything is good. Host 2 now needs to reply to the ICMP packet it received. So to send the reply back to host 1, it sends the reply to its default gateway, which is on router 2. Router 2 receives the ICMP reply packet and drops it. Why? Well, let's take a look at router 2's routing table. A quick show IP route on router 2, and we see it knows about the network for host 2, and it knows about the point-to-point network, but it doesn't know about the network for host 1. So when it receives the ICMP reply packet from host 2, it doesn't know where to send it, and so it drops the packet. To correct that, we are going to have to apply another static route on router 2. So we're going to go into router 2, and we're going to apply the command IP route 192.168.10.0 255.255.255.0 and the next hop address 10.10.10.1. So let's take a look at the routing table now that we've created that static route. Router 2 now knows about the host 1 network, and that packets destined for that network should be sent to router 1. Let's try the ping again from host 1. Well, the ping works, and we have full connectivity across the network after using static routes to inform the router of the network topology. There is also another type of static route that we can use, and I've already mentioned it in this video, and I mentioned it in the IP subnetting video, and that is the default route. So the default route exists because your router, be it a home router, a corporate LAN router, or even a border router on the edge of a WAN, cannot know every single route and IP address destination on the entire internet. Okay, there are only very few routers that can do that, and those would be the internet backbone type routers. If your career in networking and the journey that it takes you on gets you into service provider networks, you might just get to have the opportunity to work with one of those routers. But for the rest of us, our routers are generally going to need a default route. So the way the default route works is it's really just your router kicking the router decision onto the next router on the network. And then if that router doesn't know where to send the packet, it will kick it onto its default route, and so on until eventually it does reach a router that knows where to send the packet. Another way to look at the default route is it is the route of last resort. So when your router receives a packet and it's checking the destination IP address, it's going to go through the entire routing table that it has. And if it cannot find a matching entry in the routing table, what it's going to do at that point is it will send it to the default route that is listed on the routing table. Let's look at an example with our simple network. On router 2, I'm going to remove the static route that I placed on it. And with a quick ping check, we see that we have lost connectivity from host 1 to host 2. Now, I'm going to apply a default route by using the static route command. But instead of pointing to a network, I am going to type in IP route 0.0.0.0, and then I'm going to space it, and then 0.0.0.0, and then another space, 10.10.10.1. So the 0.0.0.0, the 40 routing entry tells us that this is the default route, and then the subnet mask is also going to be all zeros. And then the next hop address in this particular case is pointing to the point-to-point interface of router 1. So that is the default gateway for the router. Now, with a ping check, we can see that we have connectivity between host 1 and host 2 again. But this time it's working differently. Router 2 doesn't know about the network for host 1. Instead, it knows to send packets with unknown destination IPs to router 1. When we look through the routing table on router 2, we can see that there is now an entry for the default route at the top of the table. and the default route is specifically called out. So if we were to look at the ping traffic, what we would see is that host 1 sends a ping to host 2. In order to do that, it will send the packet to its default gateway, router 1. Router 1 knows that the host 2 network is attached to router 2, and so it sends it to router 2. Router 2 forwards the packet on to host 2. Host 2 then replies to the ping by sending the ICMP reply packet to its default gateway, router 2. Router 2 doesn't know where the host 1 network is, and so it will send the packet onto its default gateway, router 1. Router 1 knows the host 1 network and forwards the reply packet to host 1. Alright, now up to this point, static routes have solved all our problems. But let's take a look at the limitations of static routes. And then afterwards, we're going to go into what we can use to overcome those limitations. So the first issue we're going to run into with static routes is the issue of scale. Okay, right now it solved all of our problems, but we're only working with 2 routers, and each router only has 1 host network attached to it. So what happens if we add a 3rd router to the network? Well, now we have to go onto the first 2 routers, and we have to add static routes for any networks beyond the 3rd router. Or what if we add new routers or new networks onto router 2? Again, we're going to have to go to the other routers on the network and add more static routes. Now, the other thing that we're going to run into is what happens if the network changes? So let's say a router gets removed from the network, and then we have to migrate the networks that were attached to that router over to other routers. So we're going to have to go to every other router on the network and change the static routes in order to match the new topology of the network. Okay, as the network grows and as the network becomes more and more complex, static routes become more and more of a burden. So it simply doesn't scale. The other problem we run into with static routing is multipathing. So let's say we have a network of 4 routers. Router 1 is connected to routers 2 and 4, and router 3 is also connected to routers 2 and 4. There is no direct connection between routers 1 and 3, nor is there a direct connection between routers 2 and 4. Router 1 needs to send packets to a network on router 3, and there are 2 possible paths. If we configure static routes for all possible paths, one is by going to router 2, and the other is via router 4. Then router 1 will load balance or split the traffic between routers 2 and 4. If all links are working and all links are 1 gigabit links, there's no problem. But what if the link between routers 3 and 4 is a 100 megabit link? The standard static route configuration will not account for one link being slower, and router 1 will still continue to load balance across both paths, even though the packets sent on the link between 3 and 4 will travel slower. There is a way we can compensate for this in the IP route command. After adding the next hop address, we can add what is called an administrative distance number. I'll go into administrative distance when I dive into the routing table later on, but for now, know that the lower the administrative distance number, the more preferred the route. Static routes have a default AD, or administrative distance, of 1. But if I put in a command IP route 192.168.30.0, the destination network, followed by the destination subnet mask 255.255.255.0, followed by the next hop address 10.10.10.14, and then I add another number, in this case 110, now I have assigned an administrative distance value of 110 to that static route. And if that static route via router 2 has the static route default AD of 1, router 1 will send all traffic destined to router 3 via router 2. But again, circling back to the first limitation of static routes, this just adds more complexity that needs to be managed. And also, let's go back to assuming that all of the links are 1 gigabit. And router 1 is load balancing or sending packets, splitting the packet load across routers 2 and 4 that are destined to router 3. Well, what if the link between routers 3 and 4 goes down? Router 1 is not going to know that and will continue to load balance. This will result in half the packets not reaching router 3, which is going to create a problem for your network traffic. So what can we do to overcome the limitations of static routes? Well, the way we can overcome that is by hitting that like button. And also, if you're not subscribed, hit the subscribe button as well. I'm just kidding. So that aside, the way we are able to overcome the limitations of static routes is by getting the routers to monitor the network and report to the other routers what they know about the network. And together they can all build out a network topology. And the way we go about doing that is by using a routing protocol. There are a lot of routing protocols out there, and here is a list of well-known protocols: RIP, EIGRP, OSPF, ISIS, and BGP. These protocols can be classified in different ways. One way is by classifying them as distance vector and link state routing protocols. Another way is to classify them as IGP or interior gateway protocols and EGP or exterior gateway protocols. Each of these routing protocols could be the topic of its own video, except for RIP, but to give a quick summary of each protocol, I'll go down the list. Starting with RIP. RIP stands for Router Information Protocol, and it is an old and obsolete routing protocol, and I cannot imagine any possible reason why you would be running RIP in a production network today. Now, RIP has only one metric for measuring routes, and that metric is distance, or number of hops. It simply calculates how many hops from the current router to the destination router. The other thing about RIP is it has a maximum hop count of 15. So if you have a IP address, then the destination is 16 or more hops away, you're out of luck. RIP is not going to be able to get the packet to the destination. The next routing protocol is going to be EIGRP. Now, EIGRP stands for Enhanced Interior Gateway Routing Protocol, and it is a Cisco proprietary distance vector routing protocol, which means that only Cisco devices will support it, although in fairly recently, Cisco has opened up to allow other manufacturers' devices to have limited functionality for EIGRP. Now, while it's classified as a distance vector routing protocol, it actually operates in a sort of a hybrid state between distance vector and link state. And it uses a composition routing metric which calculates a number of factors: bandwidth, load, delay, reliability, and hop count. EIGRP will also look at the MTU, or the maximum transmission unit, but it doesn't factor that into the calculation. The next routing protocol is OSPF. Now, OSPF stands for Open Shortest Path First, and it is a link state routing protocol. For local area networks, OSPF is generally the preferred routing protocol, primarily because it is an open routing protocol, and so it's not just Cisco devices like EIGRP, but all devices will support OSPF. Now, the way OSPF works is it builds out a network topology by flooding the network with what are called LSA packets, and then learning about the network from other routers. Another great feature of OSPF is it gives you the ability to segment out your network into different areas. And as a result of that, OSPF really is a versatile routing protocol, and it is the subject for another video When I make that video, I will link it up above and in the description below. The next routing protocol I'm going to go over is ISIS. Now, ISIS stands for Intermediate System to Intermediate System. This is also a link state routing protocol, but it is designed for large-scale networks, such as the networks that an internet service provider might run within their own network. As a link state routing protocol, it works similar to OSPF. It builds out a topology of the network, but while OSPF sends these LSA packets on layer 3, ISIS utilizes a topology map by riding on layer 2 Ethernet frames instead of the layer 3. And the last routing protocol I'm going to go over here is BGP. Now, BGP stands for Border Gateway Protocol. It does not stand for Bridging Gap Protocol, despite what the media says. So BGP is a very large-scale distance vector routing protocol. And you might be wondering, how large? Well, the internet runs on BGP. So in short, the way BGP works is it associates what are called autonomous system numbers to networks. And there's a lot of nuance and complexity to BGP, but the way it operates is you've got iBGP, which is within an autonomous system network, and then you have eBGP, which is autonomous system to different autonomous systems. BGP really would require its own video. Now, at the time of recording this, I took a look at the criteria for various Cisco certifications, and I worked out what you need to know in terms of these routing protocols for specific certifications. So let's take a look at that. If you're studying for the CCNA, you need to know OSPF. You don't need to know all of OSPF. As I said, it's a versatile routing protocol. But you do need to know what is called single area OSPF. Now, if you're studying for the CCNP Enterprise Networking, you need to know OSPF, and in addition to what is required for the CCNA, you will need to know about multi-area OSPF. You will also need to know about EIGRP, and you will need to know a little bit about BGP, specifically eBGP. As I said, that was from autonomous system to autonomous system. If you're studying for the CCNP service provider, you also need to know about OSPF in detail, and you will need to know BGP in detail. So you're going to need to know about eBGP, iBGP, and all the different nuances of that routing protocol. The CCNP service provider will also require you to know about ISIS. Now, if you're studying for a CCNP data center, you need to know about OSPF, and you also need to know about BGP, but in a very specific context. You will need to know about that as it is used in a VXLAN deployment. And I've got videos regarding VXLAN, so you can browse through my channel and check those out. I do not see any reference to specific routing protocols in the curriculums for the CCNP collaboration or the CCNP security. Now, regardless of whether you are studying these routing protocols for earning a certification or whether it's because you need to know them for a network that you are managing, all of these routing protocols have one thing in common. They all utilize a set of metrics to determine what the best path is to a destination network, and then they update the routing protocol or the routing table on your router with that particular path. So let's take a look at that routing table. Every device that operates on layer 3, be it a router or a layer 3 switch or even your own computer, will maintain a routing table. Now, a routing table is like a map of the network. And so when a router or any layer 3 operating device receives an IP packet, it will look at the entries in the routing table and decide where to send that packet to. Now, we already took a little bit of a look at a routing table when I was going over static routes and showing you the basics of IP routing. But let's take a deeper dive into the routing table. Here is a table that I pulled from a network that I built up. As you can see, it has a lot more entries than what we've seen so far. So let's break this down. The first thing we're going to look at is the column on the left. This is a single letter code, sometimes with an annotation attached. The single letter code indicates how that route was placed in the routing table. And the annotation provides some additional context regarding how the route was placed, or some additional information about the route itself. When you pull up a routing table on a Cisco router using the command show IP route, the first thing the router will display is the guide to that letter code and the annotations. So the first one let's look at are the C and the L codes. C indicates that it is directly connected, that it is a directly connected route, and L indicates that it is a local interface on that router. So these routes will populate into the routing table simply by configuring an interface with an IP address and then turning that interface on. Another code to look for is S. S indicates a static route. As I discussed earlier on the Cisco device, this route is manually added to by the user through the IP route command. The other 3 letters that we see show up on this particular routing table are B, D, and O. 2 of these should be easy to figure out. The third you're just going to have to memorize or look at the guide on top of the routing table. B indicates the route was learned, or the router learned about that route from BGP. So B equals BGP. That's pretty straightforward. D indicates that the router was learned, or the router learned about that route from EIGRP. Doesn't make any sense whatsoever, so you're just going to have to memorize it and know that D equals EIGRP. And O indicates that the router learned about that route from OSPF. So O equals OSPF. Again, very straightforward. Looking at the notations, there is one line that has an asterisk next to its letter code. That indicates the route that is being used as the default route. It's also specifically called out above the routing table with the gateway of last resort line. There are also a couple of IA notations on some of the OSPF routes. This means that this route crosses at least one area border router within the OSPF topology, but that's something to talk about in a dedicated OSPF video. And one of the EIGRP routes has an EX notation on it. This notation says that the route was learned by EIGRP from an external or a non-EIGRP source. As we move to the right, we can see the listings of all the routes that this router knows about. A Cisco device will make a distinction between a classful route and a classless route. And if you need a reminder as to what that is, you should check out my IP subnetting video linked below. In the case of the classful routes, such as the 192.168 routes, the table just shows which IP address it needs to send the packet to in order to reach that network. For the classless routes, such as the 172.20 and the 10.10 routes, it will make a top-line entry for the classful address, and if there's only one subnet, or if all the subnets in the classful are equal, it will add a note about the classful address being subnetted, and then list the subnets below that top line entry. If the subnets are not equal, then the note on the top line entry will read that the classful address is variably subnetted, and it will list those subnets below the top line entry. After the subnet listing, it will either say which interface it needs to send the packet out of, or what the next hop IP address is and which interface to send it out of. But some of the routes also have two numbers posted next to the IP address and site or subnet. Inside the brackets, there is a slash and another number. These are very important numbers, and they show how the router decided to put these routes into the table. The first number, the one before the slash, has a very misleading name. It's called the administrative distance. Even though the name administrative distance, the name is the administrative distance, it actually has absolutely nothing to do with the distance between the router and the destination address. Cisco routers assign an administrative distance or an AD number for each routing protocol. Some routing protocols get multiple AD numbers depending on how the protocol learned about the route. Here's a chart of AD values for each routing protocol. The important thing to know about administrative distance values is that the route with the lowest AD value wins and gets placed into the routing table. So, for example, if EIGRP and OSPF both present routes to the router for a particular network, the router is going to pick, or the Cisco router is going to pick the EIGRP route and put that route in the routing table. Networks that are directly connected to an interface on the router will show up in the routing table without a number, but the AD value is 0. It's directly connected, and the router is going to trust that above anything else. A static route gets an AD value of 1. This is a route that humans have programmed into the router via the IP route command. The router is going to place a high value of trust on this route because, humans never make mistakes, right? Or perhaps it has something to do with Isaac Asimov's second law of robotics. After that, the different ADs are assigned based off of the routing protocols, but notice that an internal EIGRP route has an administrative distance of 90, while the external EIGRP route has an administrative distance of 170. Remember, EIGRP is a Cisco proprietary routing protocol, so a Cisco router is going to trust that above everything except BGP routes. But if EIGRP learned about the route from an external source, the AD number gets knocked down to 170. It could be that EIGRP learned about that route from OSPF. So if that's the case, the router would be better off taking the OSPF route. If the router cannot identify the source of the routing information, it will assign an AD of 255. Any route with an AD of 255 is considered untrustworthy and will not be placed in the routing table. All right, so I'm going to circle back to something I talked about earlier in the video, where I brought up adding an administrative distance to a static route. Now, at the time, I talked about it as a way to make it a less preferred route in the case of a slower link. But there's another way we can use this command, and that is when we're utilizing a routing protocol, we can also create sort of a backup static route or a conditional static route by assigning an administrative distance to the static route command. So, for example, we have two routes to a network. Now, one of these is being advertised to our router via OSPF. And the other route is through a static route. But we're going to prefer the OSPF route. So what we're going to do is when we configure that static route command into the router, we're going to put an administrative distance value higher than 110. And that will be the AD value for that static route. So the router is going to prefer the OSPF route because OSPF has an administrative distance of 110. Now, if for some reason that OSPF route fails, the router will still have that static route as a backup option. So that is a conditional static route. With all of this talk about administrative distance, the next number in the bracket is the number after that slash. This is the route metric. Now the route metric is assigned by the routing protocol that learned about the route. This number will vary between different routing protocols. When a router is deciding which route to add to the table, it will first look at the AD number. The lowest number wins. Then it will look at the metric number, and because at this point it has eliminated all routing protocols but one, it is then able to compare the metric values assigned by that routing protocol. Just like with the AD number, the lowest metric value wins. So this is very important to understand. A router does not compare the metrics between different routing protocols. Instead, it only compares metrics from the same routing protocol. So when a router is working to figure out which route to add to the table, first thing it's going to do is use the administrative distance value to decide on which routing protocol to use. Once it has made that decision, then it will look at the metrics of that routing protocol, and again, the lowest value will win as it decides which route it has learned from the routing protocol to input into the routing table. With that being said, sometimes after working through its processes, there might be a tie between two routes. So if you look at my routing table, there are a couple of route entries that have two next hop addresses. That's because two different routes tied for being the best route. So the router added both of them to the table. And any traffic sent to those destination networks will be load balanced across the two different routes. In other words, half of the traffic will be sent to one next hop address and half of the traffic will be sent to the other next hop address. Okay, so we have now scratched the surface with IP routing and got you all primed up to start taking a deeper dive into the routing protocols. So as I have mentioned, those are definitely topics for other videos. OSPF, as I said, is the only routing protocol specifically called out in the CCNA program. So I have already started working on my OSPF video, and that will be the next video that I put out. So go ahead and subscribe to this channel. Like this video if you've made it all the way to this point. And that will be my next video, is OSPF. So if you've subscribed, you'll get to know when it comes out and you'll be able to check out that video. I've also put some links in the description below to help you with your studying. These are going to be some resources for you. These are going to be affiliate links, so take that for what you will. And as always, keep learning, keep improving, keep studying, and I will see you in the next video.